Hello and welcome back. And this video will be looking at the power rule of differentiation along with the sum and difference rule. So first and foremost, let's remind ourselves what the derivative is. So the derivative is the limit of essentially the slope of a function. What we have is rise over run. Rise is the difference in height of the function at x, and x plus a little bit. So the run is that little bit that we've scooted over, this hair, and we want the instantaneous rate of change, the instantaneous slope right at a point. So we want that hair to shrink to 0. And there are a couple of different ways that we can write the derivative. So thus far I've just been using the prime notation, so f prime of x. But we can also express this in different ways. So we have the dy dx and this d over dx notation. And this represents essentially the derivative. So if I write dy dx, what I'm saying is that I'm taking the derivative of y, which is essentially going to be the height of a function. Or I can write that explicitly, dy dx of f of x. This just says the derivative of f of x. So the d over dx isn't necessarily a number d divided by d times x. D doesn't represent a number. This should be just a symbol. It's all connected. We can't cancel anything out from the top and bottom. It's just one symbol. And so one thing I want to point out is that over the last few videos, we've seen some derivatives of various things. So, for instance, the derivative of the identity function, which is just a straight line, well, the slope of that line is 1. Okay, we've taken the derivative of x squared, and we've calculated that to be 2x. Taken the derivative of x cubed, and seen that that is 3x squared. And we start to notice a pattern in here. Furthermore, we've taken the derivative of 1 over x, found that to be negative 1 over x squared. Another way of writing that is in fact the following. So 1 over x, that's just x to the negative 1. And negative 1 over x squared, well, that's negative 1 times x to the negative 2 power. And we can see that we've got a nice little pattern going on here. Whereas, so x is just x to the first power, but also 1, that's x to the 0 power. And we can see that we have reduced the power by 1. And here we reduce the power by 1. This could be written as x to the first power. We reduced the power by 1. But also we get this extra factor out here. Well, that's just the power showing up again. So x to the third, the derivative is 3. So we pull that power down and raise it to 1 less power. And the same applies over here. We've raised it to the 1 fewer power. 1 less than minus 1 is minus 2. And we also pulled out that number. This is essentially some of the simplest ways to take a derivative. So here, if we want to take the derivative, so again, the symbol just means the derivative of x to the n is going to be n times x to the n minus 1. And sort of a brief explanation of why this is true. We will have to plug in x plus h into our derivative. So I'm looking at this right here. If I plug, and x plus h into something that's just raised to the first power, we just get x plus h. If I square that, we end up getting x squared plus 2xh plus h squared. To the third power, we'll start to notice that there's a nice pattern going on here. If you're familiar with Pascal's triangle, this is the coefficients are just those numbers. And it starts to get a little bit messy, get a little bit long, but at the same time, because there is this nice pattern, we know exactly what's going to happen here. And what I want to point out is, essentially, if I were to chop off these last terms, what you'll notice is that we have a term out front that is the same as the power that we're looking at. And then the next term, we'll see that we have these numbers coming out. So 2, 3, 4, and we're raising x to the 1 fewer power. And then we've got this copy of h. Everything else, everything out here, has lots of h's in it. At least h squared, if not h cubed, h to the 4th, and so on and so forth. So what happens if I try to take the derivative of x to the nth power? Well, I plug it into my formula. I take the limit as h approaches 0 of f of x plus h minus f of x over h. If I plug x plus h into here, well, we already saw that we get the x to the nth power. The next term had the that power out front, x raised to the 1 fewer power, and an h. And then all of these terms in here have at least an h squared, or an h cubed, or so on and so forth. And then finally, we've got the f of x, which is the minus n. And the only reason that I'm writing all this down is because those guys cancel. The h cancels there. So I'm taking the limit as h goes to 0. After the h is canceled there, I have an n, x to the n minus 1. And all the rest of these, even because they had an h squared in them, all of the rest of these still have an h. And as h goes to 0, all of these guys cancel out. Maybe I should use red there. All those guys cancel out. And I'm just left with n times x to the n minus 1. So everything that we've just done is going to be fairly straightforward from the perspective of it's just some polynomials that we're multiplying together. Let's actually use this and see it in action. So here are a few examples. I've got the derivative of x to the 10th power. So again, I take our power up here, I bring it down, and then I take x and I raise it to the 1 fewer power. Well, 1 less than 10 is 9. That kind of looks like an A. So 10 times x to the 9th power. That's it. Here I have the derivative of 1 over x squared. This doesn't really look like x to a power until I rewrite it. So I want the derivative of x to the negative 2nd power. These two things are the same. 1 over x squared is the same thing as x to the negative 2. And when I take the derivative of x to a power, I bring that power down, and I raise it to the 1 fewer power. 1 less than negative 2 is negative 3. So there's my answer. I can simplify this without, and get rid of the negative exponent, and this would be negative 2 divided by x cubed. So all of this is making sense. Here we have the square root of x. And again, this is x to a power. This is x to the 1/2 power. So maybe this is a little bit trickier, but again, we bring down the 1/2, we bring down that power, and then we take x and we raise it to the 1 fewer power. 1/2 minus 1 is going to be negative 1/2. So I can simplify this. This x to the negative 1/2 is going to end up on the bottom of the fraction. Oops. So this is going to be 1 over 2 times x to the 1/2, which I can again rewrite as 1 over 2 times the square root of x. All this is just rewriting x to the 1/2 as the square root of x. And then finally, we've got maybe a more complicated one. I've just got a worse fraction up here, 8/5, but everything works exactly the same. If I take the derivative, this is going to be 8/5. times x to the, so 8/5 minus 1, or 8/5 minus 5/5. It's going to be 3/5. Easy peasy. When we're using the power rule for these single term polynomials, or for these x to some power, it's very straightforward, and these are the sorts of derivatives that we like to take. So the next part, let's look at the derivative of a constant function. So what does a constant function look like? If we have our x and y axis, a constant function is just a constant function. It's the same height everywhere. So there's c, and we're just going to be c across from left to right. Well, the derivative is the same as the slope. And if we think about rise over run, this line isn't rising at all. So this, in fact, has slope equal to 0. So the derivative of a constant function is 0. Maybe a slightly counterintuitive way to think about this is, for instance, 1 is the same thing as x to the 0 power. Well, what would happen if I tried to take the derivative of 1? Well, this is going to be the derivative of x to the 0 power, which is going to be 0 times x to the negative 1. But that doesn't, 0 times anything is that, well, that's just 0. But this is slightly more general. C could be anything. C could be a negative number, C could be a positive number, C could be 0. This is actually going to be a little bit more useful in the following context. So rather than just taking the derivative of a constant, we can actually look at the derivative of a constant times a function. So, and this makes, I think this is sort of intuitively, it sort of makes sense. If you were to try to take the derivative of a number times a function, I can pull that number out of the function. So if I take the derivative of c times f of x, it's the same thing as c times the derivative of f of x. And I want to go through sort of a brief explanation of why this is. And we'll actually do a rigorous proof here. So let's let f be a function. It could be any function. It could be x squared. It could be the sine of x, maybe an exponential or a logarithm. It doesn't matter. We're going to say that g of x is going to be c times our function, where c is just going to be some number. Let's find the derivative of g. Okay. Well, if I want to take the derivative of g, I have to use a formula. So the limit as h approaches 0 of g of x plus h minus g of x all over h. Well, I have a formula for g, so I can plug that in. It's going to be the limit as h approaches 0 of g of x plus h is the same thing as c times f of x plus h. And then g of x, that's just the same thing as c times f of x. And oh look, I have a factor of c in the top of my fraction here. So this is going to be the same thing as the limit as h approaches 0 of c times this fraction. So I can just pull a factor of c out of my fraction here. And we saw before that if we take a limit, limits play nicely with when we're multiplying functions together. So I can pull the c out of my limit and say that this is just going to be c times the limit of f of x plus h minus f of x all over h. And this thing right here, that's just the derivative of f of x. So I will use this rule in the next video, but this is just a brief proof of why this rule works.